This is Lesson 25 of our Calculus 3 series, Surface Area. Throughout this course, we've been looking at surfaces in three-dimensional space, and here we're going to be computing the surface area of these surfaces. To develop our formula, we want to look at the most general class of surfaces, and those are the ones that are defined by parametric equations. So if we think back to what we learned from Lesson 10, for example, we have x is a function of u and v, y is a function of u and v, and z is a function of u and v. So for example, the sphere of radius 2 we saw in Lesson 10 with this parametrization, and u goes from 0 to 2 pi and v goes from 0 to pi, takes this domain on u and v, twists it and wraps it around to cover the sphere. So we're mapping this rectangular domain onto the sphere. Now in general, the domain that we're starting with and the surface that we end up with are going to have different areas, because in general there's going to be a lot of stretching and shrinking that goes along with these maps. So the area of our domain here is pi times 2 pi, so we have 2 pi squared. But we're expecting a very different area on the sphere because of the stretching and shrinking that goes on with this mapping. So let's see how we can determine the surface area of the sphere. For the surface defined by the parametric equations, let's consider the position vector function. So r of uv is x of uvi plus y of uvj plus z of uvk. And then we can talk about r sub u and r sub v that are given by the u partial derivatives of each component and the v partial derivatives of each component. Now we know that when we're computing a u partial derivative, we're holding v constant. So essentially what we're doing is we're taking a look at this with v constant, which is going to give us a curve in three-dimensional space, and then taking its derivative, giving us a tangent vector to the curve in three-dimensional space. Similarly, taking a v partial derivative holds u constant, so we're getting curves in the other direction from our original equation. So we've got u constant, and we're taking the derivatives with respect to v, getting again a tangent vector to the curve in three-dimensional space. So both of these vectors here are tangent vectors to the surface. And we saw this back in Lesson 15 when we talked about tangent planes to parametric surfaces. And let's see how we can use them to get an approximation for surface area. Let's take a look at our original domain broken up into subrectangles, and let's follow this one subrectangle mapped onto the sphere. So a closer look takes this subrectangle, whose width is delta ui and whose height is delta vj. We're going to call this lower left corner point ui star vj star, and by now you should recognize that these stars tell us that we're going to be using this point to make some evaluations in our Riemann sum. Now with this particular parametrization of the sphere, we know that this side of the rectangle here that measures delta ui, that's getting mapped to this left side of the patch. And this left side of the rectangle, whose length is delta vj, gets mapped onto the bottom of this patch here. And what we want to do now is approximate the area of this patch. Well, how can we do that? Well, we know that we have these tangent vectors given by r sub u and r sub v. R sub u gives us the change in position with respect to a change in u. So if we start out with a change in u of delta ui, our approximate change in position is going to be given by r sub u, ui star vj star, delta ui. We multiply this partial derivative by the original change in u, and that gives us the approximate change in position. In other words, this is the change in position we can expect when moving along the tangent plane. Similarly, we take a look at r sub v of ui star vj star, and we multiply that by delta vj. This gives us the change in position with respect to a change in v of delta vj units. Again, this is an approximation to the length along the surface because this is a length in the tangent plane. So if we take a closer look at just what's happening here, in general we've got the two tangent vectors here at that point on the surface. Notice the blue is the curved surface, but what we're looking at is the two vectors along the tangent plane. So the gray part here is a part of the tangent plane to the surface at this point. So to approximate the area of the patch that's in blue, we're going to find the area of the parallelogram described by these two tangent vectors. So how can we find the area of a parallelogram described by vectors for its two adjacent sides? We use the cross product. We know that the magnitude of the cross product of the two vectors will give us the area of that parallelogram. So we want to take the cross product of r sub u at our evaluation point multiplied by delta ui and r sub v at our evaluation point multiplied by delta vj, and take the magnitude of that vector. That's going to give us the area of this parallelogram, which we will use as an approximation area to the surface patch in blue. So our summation looks like this. We're summing over I and j. We've got the cross product, and notice that these two are constants and we can pull them out of the cross product computation. So our summation looks like this, and taking the limit as maximum delta ui and delta vj go to 0, we have the double integral over that domain of the magnitude of the cross product ru cross rv with respect to area. And keep in mind that this surface area formula works for surfaces that are smooth, and by that we mean surfaces for which this cross product is non-zero over the domain, and also for which the parametrization covers S just once over this domain. So let's take a look at computing the surface area for the sphere we described above. We said this is its parametrization, which gives us the vector functions ru and rv here. So we need to take the cross product and simplify. So we're here. And now we need the magnitude of this vector. So the first thing I'm doing to simplify is pulling out a 16 from each of these terms. So I factor out a 16 and then take it out from under the radical so it comes out as a 4. Next thing I'm doing is factoring out the cosine to the fourth u from the first two terms. Notice that gives us a cosine square v plus sine square v, which is equal to 1. So then we're left with cosine to the fourth u plus sine square u cosine square u. From that we can factor out a cosine squared u, leaving us with another cosine square u plus sine square u, and that's equal to 1. So what we're left with is 4 radical of cosine square u. Now remember that the radical and the square only cancel each other when we know that cosine u is going to be positive. But we're talking about u going from 0 to 2 pi, so we can't make that assumption. We have to recognize that radical cosine squared gives us the absolute value of cosine u in general. So the double integral that we're looking for is going to be the integral of 4 absolute value of cosine u du dv, where u is going from 0 to 2 pi and v is going from 0 to pi. Now how do we deal with this cosine u in absolute value? Well, we think about the intervals over which cosine u is positive and over which cosine u is negative. We know that cosine u is positive from 0 to pi over 2 and from 3 pi over 2 to 2 pi. So the absolute value of cosine u is just cosine u. But we know that cosine u is negative from pi over 2 to 3 pi over 2. So the absolute value of cosine u is negative cosine u. So we have to break up our integral into these 3 integrals, all of which are very simple. Do a basic antiderivative, plug in the bounds, and then another basic antiderivative. So we're getting here 16 pi, and that's the surface area of our sphere. Now notice that for surfaces given by functions z equals f of x, y, we can use the same method by using parametrization, but the parametrization is going to be, instead of in u and v, we'll just keep it in terms of x and y, and then it's x equals x, y equals y, and z equals f of x, y. So that our function r, the position vector function, will look like xi, yj, f of x, y, k. And then the x partial derivative is going to be 1i plus 0j plus f sub x, k. That's here, I plus f sub x, k. And then the y partial derivative is going to be 0i plus 1j plus f sub y, k. And that's here. So the cross product of those two vectors looks like this. And taking its magnitude, we're here. So that double integral for surface area now looks like this. And remember, this is for surfaces that are graphs of functions, z equals f of x, y. So let's take a look at this example. Find the area of the part of the plane z equals 10 plus x plus 2y that is inside the cylinder x squared plus y squared equals 4. So what we're talking about now is this plane z equals 10 plus x plus 2y, and we want to know just the area of the part of that plane that's inside the cylinder. So we're talking about this elliptical area here. So here we have z given as a function of x and y, so we can use the simplified form of the integral, but we have to talk about how to describe our domain D. What is our domain over which we're taking this surface area? Well, we know this cylinder is x squared plus y squared equals 4. That's this domain here in gray. Essentially, that's the shadow we would get if the sun was shining straight down onto this elliptical surface. So here's our formula for surface area. We need to take our x and y partials of this equation for the plane. They're nice and simple in this case. X partial is 1, y partial is 2. And so we're here so far. And we need to describe our domain, x squared plus y squared is less or equal to 4, for the integral. So simplifying here, we have radical 6. And we could choose to integrate here in Cartesian coordinates or in polar coordinates. And I think polar coordinates would be much easier because we would have constant bounds for our variables. So r here is going from 0 to 2 for our circular disk, and theta is going from 0 to 2 pi. And remember, dA is r dr d theta. So we integrate with respect to r, plug in our bounds, and then integrate with respect to theta, and plug in the bounds and subtract again. We get 4 radical 6 pi. That's the area of that elliptical part of the plane. Now before we go on to the next example, I want to go back up to this formula and point out that this looks very similar to the formula that we had in Calc 2 for arc length, right? We had radical 1 plus dy dx quantity squared, and of course that was a single integral for arc length. And remember, with those problems, many of them we were only able to set up. Because of the square root, the integration gets very complicated very easily. So you can expect the same type of thing is going to happen with these surface area integrals. In that case, we'd have to use numerical methods to approximate the integral. In any case, let's take a look at another example, and this one we can solve. Find the surface area of the hyperbolic paraboloid z equals x squared minus y squared inside the cylinder x squared plus y squared is equal to 4. So let's take a look at this in the grapher. Here's our hyperbolic paraboloid and our cylinder. And we want to find the surface area of just the part of the surface that's inside the cylinder. So let's take a look at that. That's just this surface here. Could zoom in on that a little bit. And we want the surface area of this surface. So f of xy is equal to x squared minus y squared. Our x partial is 2x, our y partial is negative 2y. So plugging that into our formula for surface area, we're here. Simplify a little bit. And if we want to take a look at this in Cartesian coordinates, we set up our bounds. Here I have it set up for y and then x. Y goes from negative radical 4 minus x squared to positive radical 4 minus x squared. And then with that, x goes from negative 2 to 2. That's for x squared plus y squared is less or equal to 4. That's our domain. But this isn't reasonable to integrate. So before we give up, let's take a look at this in polar coordinates. In polar coordinates, we have 1 plus 4r squared cosine square theta plus 4r squared sine square theta, r dr d theta, r going from 0 to 2, theta going from 0 to 2 pi. Now we notice here that we can factor out the 4r squared and get a cosine square theta plus sine square theta, which is equal to 1. So this integral simplifies to just radical 1 plus 4r squared, r dr d theta. And with this, we could do a nice little u sub. U is equal to 1 plus 4r squared. Du is 8r dr. So we need to multiply in an 8 and then a 1/8 on the outside to compensate. So I just move this r over here to be out front with our 8. Now we could change this to u. We get u to the 1/2 du. Our bounds now are 1 to 17 because when r is equal to 0, u is equal to 1, and when r is equal to 2, u is equal to 17. So we have these bounds on u, so we integrate and get 2/3 u to the 3/2, plugging in the 17 and the 1, we're here. And now integrating with respect to theta, this is all a constant, so we just get all this constant multiplied by theta. Plugging in the 2 pi and the 0, we simplify to pi over 6 times 17 to the 3/2 minus 1. And that's the surface area of the hyperbolic paraboloid that is inside the cylinder. And with that, we'll complete our lesson on surface area.